Chapter 4, Three-Phase Transformers, Configurations, Connections, and Cooling. Three-phase power generation, transmission, and distribution has become the standard and is advantageous over single-phase power for these reasons. Three-phase power distribution requires lesser amount of copper or aluminum for the transferring of the same amount of power as compared to single-phase power. The size of a three-phase motor generator is smaller than a single-phase motor generator of the same rating. Three-phase motors are self-starting as they can produce a rotating magnetic field. The single-phase motor requires a special starting winding as it produces only a pulsating magnetic field. In single-phase motors, the power transferred to the motor is a function of the instantaneous current, which is constantly varying. Hence, single-phase motors are more prone to vibrations. In three-phase motors, however, the power transferred is much more uniform throughout the cycle, and hence vibrations are greatly reduced. Mainly for these reasons, it is found that generation, transmission, and distribution of electric power is more economical in a three-phase system than in a single-phase system. It is interesting to note that the development of three-phase systems evolved starting with what they call the War of the Currents era, or sometimes War of the Currents or Battle of the Currents in the late 1800s. George Washington and Thomas Edison became adversaries due to Edison's promotion of direct current or DC current for electric power distribution against alternating current, AC current, advocated by several European companies and Westinghouse Electric, based in Pittsburgh, Pennsylvania, which had acquired many of the patents by Nikola Tesla. Nikola Tesla went on to develop three-phase power systems as it is today. When considering three-phase power generation, you can assume that it's made up of three single-phase generators connected together. The generated voltage vectors are 120 degrees apart, rotating counterclockwise at 60 cycles per second. The load can be connected in various configurations. The frequency of 60 cycles per second is a standard today in North America. There used to be some 50 cycle systems or power requirements. I do believe that they are gone now, at least in North America. There is still some 50 cycle systems in Europe. This shows a Y-connected load to a three-phase generator. When looking at three-phase transformers, you may, if you're looking at them from a pure electrical perspective, they may be considered as three single-phase units consisting of a primary winding linked magnetically to a secondary winding. They become a three-phase unit by virtue of their excitation voltage and how they are connected to one another. They may also share the same core, but they may be considered electrically, at least individually. They are energized by three-phase or three voltage vectors that are out of phase by 120 degrees. And in this case, they're joined at one point, which is the neutral, and the vectors are considered rotating in a counterclockwise condition. Transformer distribution stations, with very few exceptions, handle three-phase power, and so the transformers are either three-phase units or three single-phase units in a bank. The exception to this is where two transformers are operated in open delta to supply three-phase power. The connections of three-phase circuits may be divided into two classes, star and delta. The star connection has a neutral point at the junction of the three phases, and single-phase loads may be fed from any one of the phases to neutral. Such a connection is used at some transformer stations to supply three-phase power for motors and single-phase for lighting. Delta circuits are mostly used for straight transformation of three-phase power of medium voltage range where single-phase loads do not have to be provided for. When three single-phase transformers of equal capacity are connected star to star or delta to delta, the capacity of the bank is equal to 3 times the capacity of one of the transformers. Note, when the windings of a transformer are referred to as primary or secondary winding, the winding, regardless of the voltage level, connected to the source of the power is always the primary winding. Most transformer failures fall into one of these categories. Winding failures due to short circuits, turn-to-turn faults, phase-to-phase faults, phase-to-ground, or open windings. Core faults, core insulation failure, shorted laminations. Terminal failures, open leads, loose connections, short circuits. On-load tap changer failures, mechanical, electrical, short circuit, and overheating. Abnormal operating conditions such as overfluxing, overloading, overvoltage. External faults can also damage transformers, which could lead to overloading of the transformer and cause internal damage. Not all transformers are constructed identically, but this is a typical sample of what a three-phase transformer is constructed like. They usually have the high voltage and the low voltage winding on the same leg of the iron core. This ensures that the flux lines are linked almost 100% high voltage side to the low voltage side. The device requires some type of a containment. It's usually called a tank, and it's usually filled with transformer oil of some sort or nature that will insulate the windings and the iron core from the shell of the transformer itself. The steel core is laminated, and it's usually made of sheet steel, and the laminations are usually varnished to reduce the amount of hysteresis loss in the iron core as the transformer is operating. In order to insulate and bring out the terminals of the windings of the tank, apt bushings are usually used and made of porcelain to accomplish this. Transformers are classified by their voltage, starting with low voltage up through medium voltage, high voltage, extra high voltage, and ultra high voltage. This table shows the voltage ranges for each of the classifications, and the designation of 4-wire and 3-wire means the same as star and delta connected transformers. An ideal transformer will function without any losses at all. However, in the real world, we aren't necessarily dealing with ideal transformers, although some in this day and age come close to becoming ideal. We still have to deal with the losses that happen in a transformer. And the losses are usually in the form of heat, and the heat is generated primarily by what we call the I squared R losses, which tell us that the losses are proportional to the square of the current flowing in either the primary and or the secondary of the transformer. This means as a transformer reaches its maximum capacity, it's going to generate a lot of heat, and that heat is required to be taken away from the core and from the windings in order to reduce and eliminate, if possible, the aging of the transformer. If this heat is not dissipated properly, the temperature of the transformer will rise continually, which may cause damage in the paper insulation and or the liquid insulation, which is primarily oil inside the transformer. So it is essential to control the temperature within a permissible limit to ensure the long life of a transformer by reducing the thermal degradation of its insulation system. In electrical power transformers, we use external transformer cooling systems to accelerate the dissipation rate of the heat of the transformer. There are different transformer cooling methods available for a transformer, and we're going to look at a few of them right now. Most power transformers out there are what we call liquid cooled transformers, meaning that the coils and laminated steel inside the transformer and the core of the transformer is immersed in some type of cooling liquid. These transformers have coils immersed in an insulating medium, usually oil, which serves multiple purposes. First, to act as an insulator, and second, to provide a good medium through which to remove the heat. Liquid cooled transformers cooling classes went through a major change in the United States when the IEEE standard C57.12.00-2000 adopted the four-letter designation found on modern power transformers. These four letters, usually found on the nameplate and or on the drawings or somewhere describing the cooling system of that particular transformer. And the four-letter designation is described in this manner. The first letter describes the internal cooling medium in contact with the windings. So if it was an O, it would mean mineral oil or synthetic insulating liquid with a fire point of less than 300 degrees C. K, insulating liquid with a fire point of greater than 300 degrees C, and L would describe an insulating liquid with no measurable fire point. The second letter describes the circulation mechanism for internal cooling medium. Natural convection flow through the equipment of the windings is described as an N. An F will describe the forced circulating through cooling equipment or cooling pumps. A D means the cooling mechanism is forced circulation through cooling equipment directed from the cooling equipment into at least the main windings. The third letter describes the external cooling medium, A for air, W for water, and the fourth letter describes a circulation mechanism for external cooling medium, N for natural convection, F for forced circulation, fans or pumps. So let's take an example of what you might find on the nameplate or on the drawings of a transformer. For example, you might see ONAF, cooling of the transformer, which means oil, natural, air, forced, which would mean the oil is circulating through the transformer by normal convectional methods, and the air is forced around the transformer to take the heat away from it. ON-AN, cooling of a transformer, means oil natural, air natural. These are usually the type of transformers you see hanging on poles in distribution areas where you have the oil circulating naturally through radiators, which would then circulate or radiate the heat off into the air. OF-AF, cooling of transformers, oil forced, air forced, and OF-WF, cooling of a transformer, oil forced, water forced. Unfortunately, a lot of transformers that were built and are still in service today prior to the IEEE adopting its standards 4-letter designation, and the ratings may or may not have the full 4-letter or any letters for that matter describing the cooling of the transformer. In these cases, you'll have to use your ingenuity and a little imagination to interpret the cooling rating as you will see in the following examples. This is one of the simplest transformer cooling systems. ON-AN is oil natural, air natural. Here, natural convectional flow of hot oil is utilized for cooling. In conventional circulation of oil, the hot oil flows to the upper portion of the transformer tank. This hot oil, which comes to the upper side, will dissipate heat into the atmosphere by natural conduction, convection, and radiation in air, and it will become cool, as in the case of this pole-mounted distribution transformer. In this way, the oil in the transformer tank continually circulates when the transformer is loaded. As the rate of dissipation of heat in the air depends on the dissipation surface of the oil tank, it is essential to increase the effective surface area of the tank, so additional dissipating surfaces in the form of tubes or radiators are connected to the transformer tank. ON-AF, cooling of transformers, oil natural, air forced. Heat dissipation can obviously be increased if the dissipating surface is increased, but it can be made further and faster by applying forced air to flow over the dissipating surfaces. Fans blowing air on cooling surfaces takes away the heat from the surface of the radiators and provides a better cooling than just natural air. As the heat dissipation rate is faster, electrical power transformers can be loaded more without crossing the permissible temperature limits. The heat dissipation rate can be still increased further if the oil circulation is accelerated by applying some force. In OF-AF cooling system, the oil is forced to circulate within the closed loop of the transformer tank by means of oil pumps. OF-AF means oil forced, air forced cooling methods of transformers. The main advantage of this system is that it is a compact system for the same cooling capacity OF-AF occupies, and it takes up much less space. We know that the ambient temperature of water is much less than atmospheric air in the same weather conditions, so water may be used as a better heat exchanger medium than air. In OF-WF cooling systems of transformers, the hot oil is sent to a oil to water heat exchanger by means of an oil pump, and there the oil is cooled by circulating cold water around the heat exchanging pipes of the oil. OF-WF means oil forced, water forced cooling in transformers. The windings and the core are immersed in oil. A cooling radiator is mounted externally to the tank of the transformer through which the oil is pumped. Cold water is forced to circulate through the radiator. This water carries the heat away from the device. This design is usually implemented on transformers that are used in high voltage transmission lines. The biggest advantage of such design is to reduce the size of the tank. This reduces the cost by a huge amount. Another advantage is that the maintenance and inspection of this type is only needed once or twice a year. This type of cooling lends itself quite nicely to hydraulic generating stations, where there is a constant supply of naturally occurring water that can be directed through the cooling radiators. In some cases, without the requirement of pumps, as the natural head of the plant provides ample pressure to circulate the water. Such is the case at Churchill Falls Generating Station in Labrador, where 11 535 MVA transformers are cooled in this fashion. By the way, the secondary bus connections are also cooled in this way because the amperage of the secondary connections are in the neighborhood of 33,000 amps. Air from around the transformer's secondary leads are enclosed in what we call bus ducts, and the air is fan forced through similar cooling radiators mounted externally. Cold water is forced to circulate through the radiators. This bus duct can be seen at the top of the transformers of each of these pictures. As well, each of the 11 generator stators and thrust bearings are cooled in this manner. These units that generate approximately over 500 MVA of power in a continuous fashion require a lot of heat dissipation, both from the stators, the bearings, from the transformers. So there's a lot of heat going down the Churchill River. Transformers are sometimes multi-rated depending on the type of cooling implemented. In this example, the transformer is rated at 50 MVA and should not exceed 55 degrees C if self-cooled, that is, no auxiliary mechanical equipment put into service. The transformer can then be operated or pump out 66.667 MVA but should not exceed 55 degrees C, and that can be achieved with simply the forced air cooling equipment. You can further increase the rating of this transformer to 83.3 MVA, providing you don't exceed 55 degrees C, if you turn on the fans as well as the oil pumps. And you can further rate this transformer up to 93.3 MVA, but should not exceed 65 degrees C with the fully implemented cooling mechanisms that are available. The mechanically assisted equipment is usually automatically switched on as the operating temperature rises, but it could be operator initiated. In either case, close observation is required, as this expensive equipment is operated close to the rating limits. In any event, protective relaying should take it out if limits are exceeded for too long. Here's another example of a transformer that is multi-rated depending on the type of cooling implemented. In this example, a transformer is rated at 3 different levels for the various stages of cooling that are taking place. For the OA, which is oil-cooled using natural convection or self-cooled, or you can implement a higher rating on the transformer if you engage the first stage of air cooling, which is a certain amount, or the first stage of fans being initiated. If you initiate a second stage of cooling, which engages more fans for cooling, you can increase the MVA rating of the transformer. For example, the MVA rating for OA, or the self-cooling without auxiliary equipment being used, is 24 MVA, but not to exceed 55 degrees C on the transformer. You can raise the output of the transformer to 32 MVA, not to exceed 55 degrees C, of course, if you can engage the first stage of forced air equipment. And you can further increase the output of the transformer to 40 MVA, again, not to exceed 55 degrees C, using 2 stages of forced air cooling. 26.8 MVA can be used using natural convection if you want to raise the temperature to 65 degrees C. Similarly, if you engage the first stage of fans, then you can increase the output of the transformer to 35.8 MVA, and if you engage all of the fans, you can increase the MVA output to 44.8 MVA, again, not to exceed 65 degrees C. Again, the mechanically assisted equipment is usually automatically switched on as the operating temperature rises, but it could be operator initiated as well. In either case, close observation is still required, as this piece of equipment is operated close to the rating limits. In any event, protective relaying should take it out if limits exceed a temperature rating for too long. Here is a third example and our last of a smaller transformer that has only one type of cooling but multi-rated depending on the operating temperature. ONAN cooling, which is oil natural, air natural. And you can put out about 7.5 MVA of this transformer, but should not exceed 55 degrees C in this self-cooled type of equipment. And you can go as high as 8.5 MVA, but not to exceed 65 degrees C. This ends Chapter 4.